All right, good evening, class. May I have your attention, please? So let's start. First, recall what we have learned and what is missing. Now, so I gave you two ways to design the controller. So do you know how to drive the state to 0? Do you know how to do it? Yes, right. That's what you have learned, right? We know how to do it, right? To make the x go to 0. Both the power placement and LQR can do it. If we use power placement, how do we design the pose of the desired position? How do we design the desired pose? You use the performance requirements, right? You design a reference model to meet the time domain specifications, for example, right? We have some requirements on the settling time of and the overshoot, right? You have a certain say, okay, you want the overshoot to be less than 10%. You want the settling time to be 1 second. You have those requirements, and then we have the relationships between those time domain requirements and the time duration natural frequency for the second order system, right? You design the reference model to meet those requirements. That's how we design the pose. If we use LQR, do we need to design the desired pose directly? Some of you have probably started working on the assignment, right? The mini project, then okay, you have to design, instead of the desired pose, right? You have to design the weighting matrices, Q and R. And it involves a certain amount of try and error, right, to find out the best answer. So you design those weighting matrices to strike a balance between the speed and the cost. For this one, so unfortunately, we don't have a well-defined formula, right, for you to design the weighting matrices. Okay, so if the goal, right, is to keep the system at the equilibrium point, in other words, we want to make the state variable at 0, then we know how to do it. But of course, right, and also some students ask me, we don't want the state go to 0, right? We want the state to go to some other place. So therefore, if the control objective is to keep the output at some non-zero constant, for example, if the error conditioning, right, you want to set the depends upon different preference, right? Some people like to set at 26 degree, and others may want to set at 23 degree. So you want to keep the output at a different constants, right? That's what we call the regression problem. Or sometimes not even at the constant, we might want to make the output, right, to track a time varying reference signal for some applications. Okay. And here I will just give you a sense about what kind of application we want the output to track a time varying desired output.
Coming in, Ice, coming in. Ice, that bogey's still behind you. I'm maneuvering for a shot.
Stay with him, man, stay with him. Take the shot, nail him, nail him.
Shit, Ice, I can't get a tone.
Shoot, Maverick, I can't get him off my tail. Maverick, we're hit again.
It's okay.
All systems are functioning, we're okay.
Ice, on the count of 3, brake hard right. 3, 2, 1, brake right. Firing. Damn it, missed.
Don't let him go. Keep on him, Mav, keep on him.
I got him. Here comes the shot.
So the missile control systems, of course, we want to make the missile hit a moving target. Okay, we know that both the power placement and LQR focus upon how fast we want the system to behave, or in other words, the transit response, right? When we, you see, in those design examples, we just say, okay, what is overshoot? We wanted the system to tolerate. What is the settling time? You wanted the system to respond, right? We didn't mention how accurate you wanted the output to be, right? Okay. Today, so we are going to focus on the other factor for the control systems, of course, which is very important, is accuracy. We want to know how accurate is the real output, follow the desired output. That point we didn't mention in the past 2 weeks, right? The past 2 weeks we want the output to go to 0, but here that's we want the output to track a reference output. So R is the reference output. Then you get the difference between the desired output, right, R, and the actual output. That's what we call the output error, right, E. Okay, so this is the measure of the accuracy. And what we can achieve is what we want to see. At the beginning, maybe the output error is big, but eventually, right, after a while, we want the output error to go to be very small. Eventually, it converts to 0 at steady state. So that's what we want to achieve, right? How are we going to design the controller to achieve this goal? And also, meanwhile, we also will consider the impact of the disturbance. So there may be some disturbance affecting the system, like a wind blowing on the antenna, right? Those kind of things we want to consider that. So even with the disturbance and also the reference signal, right, may not be necessarily a constant. I just show you the reference signal may be a time varying signal. Or if a robotic arm, you want to make it, follow a periodic motion, you design your reference signal as a sinusoid. Okay, so of course, the ideal situation is that we can make the output follow the desired one, right, equal to R at every time instant. But that is too ideal, right? Normally, in many situations, it is impossible unless you have a perfect information. Okay. So what we want to achieve, instead, right, we say, okay, I don't want the output to follow the desired output immediately, right? But at least I want the output to follow this desired output when time t goes to infinity. Of course, here mathematically we say goes to infinity. In reality, just means after a while, right? After a while, the difference will be very small. When we're talking about the isotopic tracking problem, we first solve the case where that your reference or the desired output is not a 0, right? It may be a time varying signal. Okay, but the disturbance is 0. Okay, this is what we call the asymptotic tracking. Of course, you want to know, hey, what happens if there is disturbance? We have to deal with the disturbance. Sure. For disturbance rejection problem, we call asymptotic regulation. For this problem, we just for simplicity, we assume that your desired output is 0, right? We want to design a controller such that the output, right, will also go to 0. You can say the difference between the desired output and the actual output, right, will approach 0 when the disturbance is not 0. So we want to know how to do it. This problem is called the asymptotic regulation problem. Right? Once you can design a controller to achieve both, remember, if you can achieve both, eventually it can follow some reference output, and also meanwhile it can also minimize the impact of the disturbance. Okay, this is what we call the servo control problem in the nature. When we call servo control, we say, okay, we want the output for some desired output, non-zero output, and also we want to reject the influence of the disturbance. Okay, so far, so right, for the past 2 weeks, we only focused upon to design the controller, right, such that the whole system is stable. So therefore, the output will go to 0. But here today, so we are going to talk about the general case. That's also the case for the real control systems. We want output, right? Of course, for many control systems, the desired output is indeed a constant. But for some applications, okay, the desired output is a time varying signal. All right. So how are we going to do that? So we're going to show you today. But before I present the solution, let's just draw some tips on how we did it, right? For a simple case. So when you assume that many of you took a course on control system design, if you look at this diagram, right, that should look very familiar to you. You have a system, right, describe a transfer function, okay, and then you have some reference output. You want the output Y to follow. Okay, you get the difference. That's the error signal. You design a controller. Okay, and when we talk about the integral control, right, I just extracted the integral from the controller. Just means, right, if you combine those two, it means that there is an integrator in your controller. Okay, but we want to emphasize the role of the integrator to achieve the zero steady state error. With an integrator, we can make sure that those error signal, the difference between the reference signal and the output, right, this error signal can go to 0. But we need an integrator. Okay, that's what you have learned when you were undergraduate. But let's try to understand why do we need an integrator. And then we are going to follow this idea. I want to extend this idea to deal with a very general case where the reference signal may not be a constant, right? Maybe a time varying, maybe a sinusoid. Okay. Now, let's try to analyze this configuration. We try to understand why this error signal has to be 0 at the steady state. You can say there is a condition, right? The closed loop system has to be stable. If the closed loop system is stable, it is guaranteed that the error signal will go to 0. Okay. Now, let's do the analysis step by step. If the whole system is stable, for a stable system, and you have a constant input, the R is a step signal, right, is a constant. What will be the output? Well, the output will be a constant or a time varying signal? Has to be a constant, right? Has to be a constant. You have learned that. Okay, we know, therefore, which means all the signals, if the input is a constant and the system is stable, we know at the steady state or when time t goes to infinity, all the signals, right, will converge to a constant. All the signals will settle down to a constant. Okay. So now let's just zoom in on the integrator. So here we say that if we just zoom in on this integrator, at the steady state, we say, okay, this is a constant. The output will be a constant. And we also know, okay, this is also a constant. Let's say another constant, we say C1. Okay, this output go to C2, right? All the signals will convert to a constant. But remember, this is a integrator, right? Integration means summation, means summation. Think about that. We know this is a constant, and the output is also a constant, does not change. The output will not change. Now, there is a very special property about this constant. So, because we know it's a constant, the only two cases are whether it is a zero constant or non-zero constant. Okay. Now, imagine if this is a non-zero constant, right? And then you do integration. A non-zero constant, right? You do an integration. And when t goes to infinity, right? You do an integration. How about the output? Cannot be a constant, right? You continue to add something. So therefore, it cannot be a non-zero constant. If it's a constant, it has to be zero. Is that clear? Right? So that's a magic power of the integrator. It has this special property that at the steady state, where all the signals settle down to a constant, it's guaranteed that the input to the integrator will be zero. Okay? All right, so what's the constant input to integrate at steady state? I already explained to you, it has to be zero. Otherwise, the output cannot be a constant, right? Okay. So you can say from this one, there are two key components, right? First one, there must be an integrator to deal with if the desired output is a constant. We should have an integrator in the controller. So this is what we call is we have to have a right servo mechanism to make it work. Now, another also very important factor is the whole system or the closed loop has to be stable, right? If the closed loop is unstable, we cannot make any judgment because the signal may blow up. If the signal blow up, of course, the input may not be zero, right? The system has to be stable. Okay, so there are two elements to make it work. We have to have our integrator, okay, in the control system, and we have to make sure that the whole closed loop is stable. Okay, any questions? So that's what we have learned in the past, right? Now, so today, we are going to extend this idea to deal with the case where your reference output may not be constant. Therefore, adding an integrator to the system may not be sufficient, right? We have to add something else. All right. So we are going to extend the idea, right, to to deal with general type of reference inputs, right? R can be time varying function. And also, in this configuration, of course, right, all the signals are scalar, right? The output is one number, right? The reference output is also one number. Here, of course, we want to generalize to the multiple input and the multiple output system. Okay, so today we are going to learn those two parts. And we know we can solve the problem, right? If we can have a right servo mechanism for any given input type, and also we know how to stabilize the closed loop. Okay, so therefore, roughly speaking, the servo control design, right? There are two parts. One is servo mechanism. The other one is stabilization. So we are going to discuss how we're going to do it when we only have a transfer function, right? And also there is only one input and one output, but the reference output may be time varying. And then later, we're going to extend it to the multiple input and multiple output case, right? Then we're going to use the state feedback to achieve that. Okay, here, I give you, so we are going to use our industrial example to show you how to design it, right? In this industrial example, right, it is about the satellite antenna, right? If you, I think many of you probably noticed this, right? In many of the places you saw this, you need to know, okay, that is the antenna which can move, it moves. Why you want to make it move? Because you want to make this antenna to track the satellite. Okay, here I just give you the motivation for the striking controller design. Okay, here is a short video clip about the satellite technology and the antenna.
A heavy metal ball with 4 strange-looking rods started everything. All it could produce was a funny kind of sound. It may not seem too impressive, but please know that thanks to that metal ball, you are able to sit down and watch a sports match coming live from the other side of the world and know whether to take an umbrella when you leave home tomorrow morning. Sputnik, the first man-made satellite, launched by Soviet scientists in October 1957, was not capable of doing much. But Sputnik will forever be remembered for paving the way to the satellite revolution, which changed our world forever. Satellites stay in orbit thanks to Earth's gravity. In low altitudes, a satellite must maintain a speed of no less than 8 kilometers per second in order not to fall back to the ground. The satellite's relative speed vis-a-vis the Earth is determined by its distance from it. Low-orbit satellites circle the Earth once in an hour and a half. Satellites in a medium Earth orbit do so twice a day, and geostationary orbit satellites take exactly 24 hours to circle the Earth and therefore appear to be hanging over a fixed point on the ground. 3, 2, 1.
Liftoff.
The most dramatic stage of the satellite's life is the launch. Years of development and strict preparations are concentrated in these crucial moments. The launching missile, composed of 3 stages, sheds the first 2 heavy ones in the first few minutes in order to obtain maximum speed when entering space. As it reaches space, the satellite separates from the 3rd stage and sets up for operation. Its solar panels and antennas are deployed so that it can use the sun's energy. Photographic equipment and other systems also begin operations. Low Earth orbit satellites are used mostly for imaging purposes, both civilian and military. These satellites orbit the Earth about 15 times a day and can obtain either individual frames or strips of photos while maneuvering to change their angle until they complete a scan of the desired area of interest. These satellites are extremely valuable. They can detect military movements over time, assess ecological or geological changes, assist in agriculture, mapping, and much more. They give us a snapshot of our world from different angles, free of territorial limits and in real time. In medium Earth orbit, 20,000 kilometers above ground, the satellite requires 12 hours to circle the Earth. At this altitude, a constellation of 25 GPS satellites provide navigational aid to millions of people around the world. Military forces can find their way in the field and accurately direct GPS-guided missiles to their targets. Commanders in the headquarters can receive a live status of the whole battlefield. Global positioning satellites cover the Earth so that at each given moment, a GPS device on the ground receives at least 4 positioning signals from orbiting satellites. The point in which just 3 signals cross each other yields an accurate coordinate on the ground. Combined with a mapping software, the result is the familiar moving GPS image we know. At an altitude of 36,000 kilometers, it takes exactly 24 hours for a satellite to circle the Earth. This synchronous orbit hosts a ring of geostationary communication, weather, and early warning satellites which are positioned over fixed points on the ground. Geostationary satellites can connect large remote areas on the ground. They transmit to the ground in beams. Each satellite may transmit several beams directed at various places on Earth. The area that each beam covers is called a footprint, and all the antennas contained in this.
Here are the antennas, right? It can receive the signal from the satellite. Then you have to, the antenna has to move its position such that it can, in a best position to communicate with the satellite. That's the control problem we're going to solve.
This area can enjoy its services. Geostationary satellites are used for various communication forms. Direct-to-home TV channels, broadband internet, satellite radio, telephony, e-medicine, e-learning, and much more. These satellites play a major role in the communication revolution our world has experienced in recent years. They are.
All right, so we have to, control the position of the satellite, right? So how we going to do that? And we know it is not a constant. We may have to move because the satellite is moving sometimes. So therefore, we want to control the elevation of the antenna designed to track a satellite. Okay, and of course we can easily use the Newton's second law, right, to model the position of the satellite, right? This theta is the angular position, right? J is the moment of inertia, and here B is the damping, and this TC is the net torque from the motor, and now here is the TD. TD models the disturbance. So, right, probably suddenly there may be a wind blowing on the antenna, or can you deal with that kind of disturbance? Okay, and then let's say we do some change of the parameters to simplify the model, and finally we may just have a very simple model like this. So the prompt is describe a second order system, right? The A is some parameter. In this case, there's A equals 0.1, and we know that, of course, the system is not stable. We want to stabilize it, and then we want the theta, right, the position to track a desired output. Okay, so how are we going to do that? So we are going to return to this example, right? After we have learned the general way for doing this. Okay, so this is just a motivation for you to say the usefulness of servo control. Okay, We'll first give the solution, right? For the case where there is only one input and one output. So because, right, the reason is simple, many of you already know how to do it when the reference input is constant, right? We have an integrator there. So it's very natural to extend that solution for the general case where the desired output or maybe a time varying signal. So after that, we're going to present the solution for the state space model. Okay, here is what we call, if there is only one input and one output, okay, one input, one output, you are given the transfer function G. This is what we call a unit output feedback system, right? So here, because in this link, right, there is no transfer function there. It's just a kind of with a gain of 1, right? So that's what we call the unit feedback, output feedback. So what we want to design is this part, the controller K. You can design any controller, right? And the objective, we want to make the error signal go to 0, okay? But the R will not be necessarily a constant anymore. It may be a time varying signal like a sinusoid. And also there may be some disturbance. Those disturbance may not be necessarily a constant. Okay, there may be some sinusoidal wave, okay? So when you were undergraduate, right, you have learned the solution when the disturbance and the reference signal is a constant, you know, okay, you just put an integrator in the controller. But here we say, okay, for the general case, what kind of controller should we design, okay, to achieve the goal, right? Okay, let's go to the mathematics. So what we know is the transfer function is given, G. So which means, okay, we use N, right? That's a symbol for the numerator, right? D is the first symbol for the denominator. So we call NS over DS. N and D are given. What you can design is a transfer function for the controller. We use B over A. So B and A are the design parameters or the polynomials you want to design. And the closed loop transfer function from between the reference input and the output can be easily, right, computed by this formula. So let's go back. Remember here is G, this is K, right? We say the formula is, this is the open loop. There is a formula to get you from numerator is the feed forward transfer function, right? So it's K times G. Denominator is the 1 plus the open loop transfer function. You say, where is the open loop? So you disconnect this, and then it becomes the open loop. So the open loop transfer function is also K times G. So that's the formula you can use, right? Of course, if you're not familiar with the formula, you can verify it by algebraic calculation that this is the case for the closed loop transfer function. Okay, so let's just plug it in. The expression for this Planck transfer function and the controller, right? We will get the closed loop transfer function. Takes this form. Of course, we know that this is the denominator of the closed loop transfer function, right? And the way that we know that the poles of this transfer function, which means that the roots of the denominator have to have negative real parts. All the poles has to be on the left side of the plane, right? Okay, so therefore, the problem becomes if you're given D and N, and then you want to choose A and B, such that, let's say you want to make the system stable. Now, if you look at the formulation of the problem, Can we consider it as a pole placement problem? You want to place the poles of the closed loop to some desired position, right? Let's say for at least those poles have to be stable. We don't require the original system to be stable, right? What we want to is this closed loop system to be stable. So we have already solved the pole placement problem, but at that time, right, in chapter 7, we didn't use any transfer function, right? We used the state space model and we did it. So now we need to solve with transfer function. Okay, so it's a new solution, but the solution is also as simple as the one we have done for the state space model. Okay, let's first look at one specific example. Here we have a first order system. Is the system stable or unstable? Because this one you have an integrator, we know integrator is not stable, right? Okay, all the poles have to be switched on the left half of the plane. So when we choose a controller, we should always start with the simplest one. So what is the simplest controller you can imagine? Proportional, right? Proportional. So the controller, the transfer function is a constant gain. So let's just plug in, okay, say the controller is just a simple gain, proportional control, and then you plug it in, K times, right, this transfer function, this is G, and then we'll end up with the transfer function of the closed loop in this form. You just pay attention to the denominator. Is it possible to design the K such that the closed loop is stable? Yes or no? Of course, right? Of course, actually, if you are familiar with the second order system, you know any positive gain can do it up. Any positive K will make sure that the poles of the system are stable. But can we place the poles to any desired position? Okay, for example, let me say we want the desired poles are -2 and -3, right? So we want to design the K, right? Design the K such that the poles are placed as -2 and -3. So these are the desired polynomial we want to match. Is it possible to design the K to make this happen? Of course, right? No matter what you do with K, the middle, this coefficient cannot match this coefficient, right? Okay, so it's an impossible job. Clearly, we cannot find the controller to meet this goal. It doesn't work because in this controller, right, there is only one parameter for us to design. Okay. Then we realize that the controller needs more degree of freedom. So how do we add more freedom to the controller? How can we get more design parameters for the controller? What should we do? You are free to design a controller. If the proportional controller doesn't work, what should you do? Right, just to make it more complicated, right? To increase the complexity of the controller. So the proportional control we call it's a zero order, right? It's just a constant. Now, the next step you want to try is the first order controller. Okay, for the first order controller, the numerator and denominator are just a polynomial with first degree. Okay, now you can say, actually now you have 4 design parameters, right? Previously you only have 1. Okay, and then let's try this, right? Then we plug it in to the closed loop transfer function, right? And then we'll end up with this final expression for the closed loop transfer function. Of course, we'll realize, right, this desired, this one, right, the order is 3. So when we design the desired polynomial, the order has to be 3, right? Otherwise, we cannot match. Okay, so we design the desired closed loop polynomial, right, as this one. Of course, how we specify those F1, those coefficients, of course, are decided by the desired poles, right? You can compute that. You know the desired poles, you plug in, you get those coefficients. But you know, in this one, you have to design 3 desired poles, right? So normally, you can design the pair of the dominant mode and the third pole far away from the dominant mode. Okay, therefore, we try to, so those coefficients are given. This is the desired one. You want to design those parameters of your controller to match. So certainly, right, there are 4 coefficients to match. Then you have 4 equations. Then there are 4 design parameters, right? So easily you can solve the equation and get the answer. Okay. Let's just work out a specific example. Let's say I want to place 3 poles, okay, -2 and a pair of complex poles. Then we can work out the desired closed polynomial. This is the polynomial we want to match, right? And then for this set of poles, we can compute the A0, A1, B0, B1, okay? And then this will be the final controller. So now, the first we try the proportional controller. It doesn't work, then we can increase the complexity of controller. So what we have learned, we say, okay, if we use the higher order of controllers, we will get more free design parameters. That will give us better chance for the power placement. But on the other hand, remember, right, the higher the order of the controller, of course, your controller will be more complex. It also means more cost, right, when you implement that. Then there are some other questions. Now, can we always get the solution to the power placement, assuming we have the sufficient complex higher order controller? Can we always get a solution or not? Then, what is the proper order of the controller? Well, now we'll look at the general case, and we will find out the condition for achieving power placement with the transfer function approach. Okay. All right, so here, this is the unit output feedback system while we are considering for the servo control problem. Then, okay, we know the transfer function of the plant, and then we are supposed to design the transfer function for the controller, B over A. In the general case, okay, we say the order of the process, we know, of course, that is the degree of the denominator, right? We say is n, and also require that the transfer function is proper. Okay, the degree of the numerator cannot be bigger than the degree of the denominator. And then we can get the closed loop transfer function, right? This is the formula. This is G times K over 1 plus G times K. We plug in the expression of the G and K. So this is the expression of the closed loop transfer function. Then the power placement problem is equivalent to solving this equation. So we want to find out the A and B. Those are the polynomials of S. So where the D and N are given, we try to find out A and B to match our desired polynomial. the roots of this desired polynomial are the desired poles of the overall system to achieve. You, of course, you know where are the desired poles. You design the desired closed loop polynomial, and then you want to design your A and B to satisfy this equation. Okay, then there are a number of questions. Are there solutions? Okay, what are the conditions to assure there are solutions to this equation? And what is the order of the controller? How to find out the solutions? And the third question is, are the solutions realizable? Can we implement the solution? Okay, to address those questions, first of all, we try to define there is a concept of coprime of two polynomials. Okay, when we say, of course, when we say those two numbers are a prime, right, coprime, then we know what does that mean, but here is just a generalization. We say, okay, there are two polynomials, alpha and beta. They are coprime if they have no common factors. Okay, it's just like you have two integers, right? How do we know that there are two? They are coprime, right? If they don't have any common factors in those integers. Okay, so here, look at those examples that are quite straightforward. We say, okay, one polynomial is s plus 1 times s plus 2. The other polynomial is s plus 3 times s plus 4. Okay, those two polynomials, they don't have a common factor. Therefore, they are called to be coprime. Okay, but here we look at the second example. P1 is s plus 1 times s plus 2. P2 is s plus 2 times s plus 3. And we notice, okay, those two have a common factor, s plus 2, right? Therefore, we say those two polynomials are not coprime because they have a common factor. Okay, is that clear? Okay, now let's talk about the condition for the existence of a solution. So let's first take a look at one simple example. The example shows that what could be the consequence if there are common factors in the transfer function of the system. So we say if D and N, those are the polynomials of the transfer function of the system, right? If that contain a factor, a common factor is minus 2. In other words, right, ds can be written as a s minus 2 times a d bar, another polynomial, and n can be written as s minus 2 times another polynomial n bar. Okay, and then let's write down the equation we try to solve, right? This d times a plus n times b. Okay, plug in the expression of d and n. Both of them have a common factor, so let's take out this common factor. Then this equation, right, becomes this common factor times the bracket, those d bar a plus n bar b, right? Okay, so here, now let's look at this equation. This are the closed loop polynomial, and on the right side is the desired polynomial you want to match. And what are the design parameters? Well, the design parameters are those two polynomials a and b. D bar and n bar are given. Okay, but you are free to design any possible polynomial a and b. Okay. Now, here is the question. Is it possible to choose a and b, that polynomials, right, to match any desired polynomial? For example, let's choose, right, the desired polynomial to be in this form. Now, all those stable poles are placed at minus 1, minus 2, minus 3. So therefore, let's just write down the expression of this equation such that you can clearly say the answer. Okay? D bar, n bar are given polynomial. A and b are the polynomials you want to find such that this left side of this polynomial can match the polynomial on the right side. Is there a solution? Okay, there is no solution. Why? Because on the left side, there is a root of 2. On the right side, there is no root of 2, right? No matter what you do with A and B, it does not affect this root. Is that clear? Right? Okay. So it's therefore to make those two polynomial match, right? We on the right side of the polynomial or the desired polynomial must have this -2, s -2. Otherwise, it's impossible to solve this equation. So therefore, we can conclude if n and d have a common factor, then not every root of the closed loop polynomial can be arbitrarily assigned. Okay. So also, which means the root correspond to that common factor cannot be changed by the controller. Now, therefore, to have a solution to the pole placement, if we want to place the poles to any place we like, right, we have to assume that D and N are coprime that don't have a common factor. Okay, and it turns out this is the only condition we need. So that is the necessary and the sufficient condition for the existence of solution. Okay, the transfer function does not have a comma, pole, and 0. Now, the second question we want to address is, what is the order of the controller such that we can find out a solution? Okay, this answer to this question can be easily found out by examining the number of the design parameters and the number of the equations we can get. Okay, so let the order of the system be n, which means the degree of these two polynomials, right, are n. So particularly Dn cannot be 0. Okay, and then let the order of the controller be n. So therefore, we write the highest degree of this polynomial, right, with a degree of Sn. Okay, so and you are free to design those coefficients of those polynomials. Now, because we need to solve an equation which involves, right, d times a plus n times b. We want this polynomial to match a desired polynomial, right? Let's first check out the order of this closed loop polynomial. If the degree of d is n, the degree of a is n. So what is the order of the closed loop polynomial? Has to be n plus m, right? The order of the closed loop is m plus n. Okay, because the order of the closed loop is m plus n, therefore the desired polynomial, of course, have to be of order n plus m. Otherwise, they cannot match, right? Cannot be bigger than m plus n. So let's put the desired polynomial in this form with an order of m plus n. Okay, and then let's try to match. So this is d with a degree of n. This is a with a degree of n, right? D times a plus n times b equals the desired polynomial with a degree of m plus n. Okay, and then we need to expand this out and organize all the terms into a one polynomial. Right. Now, and then we need to match, right? To make those two polynomials the same, right? All the coefficients should be equal to each other. So how many equations can you get? Because, right, you look at the coefficients, there are m plus 1, right? That's the number of the equations you can get by matching the coefficients, right? Okay, then you compare the two polynomials. Actually, we will have m plus n plus 1 equations. Okay, and then we can even write them into a nice compact form, right? In terms of a matrix times a vector equals another vector. But let's just check out how many unknowns are there, right? Those are the design parameters. We want to find out the values. Okay, in these equations, right, we know there are n plus n plus 1 equations. That's why it has n plus n plus 1 rows, the number of equations. And those are the number of the design parameters. Of course, they have A has n plus 1, right? B also has n plus 1 total. We have 2 times n plus 1 design parameters in this column of vector, right? Okay, now from the linear algebra, you have learned what was kind of a common sense, right? What is the maximum number of equations allowed for existence of a solution? If you compare the number of the equations and the number of the unknowns, what is the condition for you to find out the solution? The number of the equations has to be equal or lower than the number of unknowns, right? So the number of equations cannot be bigger than the number of the design parameters. That is kind of common sense, normally. So which means this one n plus 1 has to be less than or equal to the number of the unknowns. In this way, we get the number of the unknowns m, right? The degree of the controller has to be bigger or equal to n minus 1. Okay. All right. Then we know that the order of the controller has to be bigger than or equal to n minus 1. Okay. And if the d and n are coprime or have no common factors, actually we can prove that this matrix will be of 4 rank. Okay. But of course, we don't have time to prove that in the class. But just for your information, this one, if they have no common factors, we can always find out a solution. Now, in this case, if the coprime, right, and if n equals n minus 1, then that matrix will be a square matrix, a non-singular square matrix with the order of 2 times n. Then there will be only one solution, right? Okay, you can easily get, it's like in the linear algebra, you have ax equals b. How do you get x, right? You just take an inverse of that matrix, then you can get the solution. So if n equals n minus 1, we'll have only one solution. If n is bigger than n minus 1, which means right, the number of the unknowns will be bigger than the number of equations. Then how many solutions can you find? For example, you have 2 unknowns, but one equation like this. How many solutions can you find? Infinity, right? So there will be an infinite number of solutions. Of course, to select the best one, right? Probably you need to use other performance requirements, right, for you to find out the best solution among all the possible solutions. Okay. Finally, this one, are solutions realizable? So why do we require the solution to be proper, right? Okay, when we say a rational functions, we say what we call a function is proper. So if this rational function is in this form, typically for a transfer function, right, it will be a one polynomial divided by another polynomial. Alpha is called proper if the degree of alpha is bigger or equal to the degree of the numerator, beta. For example, right, s plus 2 over s plus 1, right, this is proper, while this one, the derivative term, right, is not proper. If the degree of alpha is bigger than the degree of beta, then we call it the function strictly proper. For example, this one we know it's proper, but those two degrees are the same, right? Both of them are 1, so it is not strictly proper. If we have this transfer function, the degree of this one is 0, this is 1, this one is strictly proper. Is that clear? But then the question is, why do we require the transfer function of the controller to be proper? So to understand this, let's take a look at the transfer function in the discrete time domain, because that one is very simple for you to know why the transfer function of the controller cannot be improper, like this one. Let's say we have a controller in the discrete time, or they transform, say, so this one, right, we know the degree of the numerator is 1, of course, the degree of the denominator is 0, right? So it's not proper. This transfer function is not proper. What could be the problem, right? We know in the Z domain, right, this is the input signal, right? This is the transfer function of the controller. So the input is the transfer function of the controller times the error signal. Now then, because K is there, right? So it's there times the error signal. Okay, this is for the Z domain, for the, okay, but also, so this one, if we write the equation in the time domain and we know Z is a forward shift operator, in the time domain we have this equation. So this will be the controller for the time domain. Now, if you look at the expression of this controller, is it possible to implement this controller? This controller means, right, you just interpreted K as the present. K means the present. K plus 1 means the signal at the next step. So the current input depends upon the output error in the future. So there is a causality problem, right? Because this one, K plus 1, is not available now. Okay, is that clear? So in this case, this is the example for you to see why if the controller is improper, we may have a implementation problem. Okay, the present output, right, UK of such controller makes use of a future output tracking error, which of course is not available at the present time. We cannot use that. So therefore, it's not possible to implement such kind of controller in the real world. So we cannot use it. With a similar argument, the present output of a proper controller will make use of the present and the past inputs. So if the controller is proper, we can implement, or we can make sure that all the signals are available now. Now let's state the theorem 1 for this chapter. We consider a unit feedback system with a proper prompt transfer function. So this G is proper with the degree, right? We know the degree of the system is N, and also we require that N and D are coprime. They have no common factors. Those are the conditions. Remember, we don't require any condition on the stability of the open loop. right? The system may be stable or maybe unstable. Okay. Now, if the degree of the controller is bigger than or equal to n-1, then for any polynomial of degree n plus n, we can always find a proper compensator, K equals B over A of order m, such that we can place the poles, right, to the desired one specified by the desired polynomial PC. We always have a solution. If you just want to get one solution, then we put the degree of the controller to be n-1. There's only one solution. If the degree of the controller is more than n-1, then you may have multiple solutions. Okay? So, has this theory answered all those three questions? Right. First one, question one, are there solutions? What is the condition? What is the condition? N and D have no common factor, right? They have to be congruent. What are the resulting controller and its order? What's the order of the controller? Should be n-1 at least. Okay. Are there realizable solutions? Yes, right. The solution will be proper. Okay, now let's look at the second example. So here, right, the transfer function is given. Of course, we know that this transfer function is proper, right? Is this transfer function strictly proper? It is also strictly proper because the degree 1 is smaller than 2, right? Okay. Of course, they have no common factors clearly. Okay. N equals 2. Now, if we just want to get one solution, what is the order of the controller? Here, n equals 2. So what is the order of the controller? 1, right? n-1. Okay. Then you know, okay, it means that the controller is first order, right? The degree of the polynomial is just 1. So there are 4 design parameters. Okay. And then you try to find out what is those design parameters. Therefore, of course, you need to know what is the desired polynomial, right? We know this degree is 1, the degree of the system is 2, so the degree of the desired polynomial must be 3, right? You have 3 poles. So let the 3 desired poles to be in this form. Okay, so that right, you get this one, you compute the desired polynomial. So therefore you plug in the poles, right? Desired poles, you get the polynomial. And this is the polynomial you want to match, right, for the closed loop. Okay. Now, how do we solve this equation, right? We know this is one way. If you prefer to use the matrix calculation, you can do it in this way. The other way is that, of course, you just plug in the expression of A and B, you compare the coefficients, right? You have a set of 4 equations. You try to solve those equations by hand instead of using the matrix calculation. Okay. But anyway, so no matter what you do, right, you can easily find out the solution of those 4 parameters. Okay, and then you plug in the expression of B and A. Okay, you get the simplified version of this controller. And then we can compute what is the overall closed loop transfer function. You can say that certainly, right, this one will match the desired ones, the desired polynomial, right, that will match the desired poles. Okay, we note that for the 0, 1 is for the pole placement. that we want to place the poles to any desired position. Now, but sometimes it may happen, right, that the systems, right, the original transfer function of the plant may have some common factor. Okay, and we know there is a condition they should not have any common factor. If they have those common factor, we know that that common factor cannot be changed, which means that pose cannot be changed. Okay, but if the purpose, right, of the controller is not to place all the poles, you just try to make it stable, right? If that's the case, then as long as those common factors are stable, it will be okay, right? Okay, so so here we can allow the D and N have some stable common factors if that's the case, but we don't allow them to have unstable common factors. Okay, first of all, let me show what would happen if a common unstable factor. So if D and N both contain the factor S minus 2, right? So D equals S minus 2 times D bar, A equals S minus 2 times M bar, and then this is the closed loop polynomial. So you can say that this closed loop polynomial always has a unstable pole, right? No matter what you do with your A and B. So what does that mean? It means that your closed loop is stable or unstable, because the closed loop always has an unstable pole, right? No matter how you design your A and B, this unstable pole is always there. So the system is unstable. Of course, that is not what you want. Okay. So in this situation, right, it is almost hopeless. Okay, unless you make some change to your hardware, you switch to a more effective input. Okay. Now, but on the other hand, if D and N both contain a stable factor S plus 2, right, then we say actually this S plus 2, right, will be a factor of the closed loop polynomial. But this factor is a stable factor, S minus 2. So it will be stable as long as this one, of course, this closed loop polynomial has to be stable, right? You choose your A and B such that A times D bar plus B times N bar is stable, right? Of course, we know it is possible, right? Because we know D bar and N bar, they are coprime. You can't place any poles, right, of this polynomial. And although this pole S equals minus 2, this pole cannot be changed by the feedback controller, but we know it is stable, right? So there is no problem. Therefore, we have this result. Consider the unit feedback system. Right now, we relax the condition that such that in the original condition, we require this N and D has no common factor, but here we say, hey, they may have common factor, but as long as this common factor is stable, or in other words, right, they don't have any unstable common factor, then we can always find a controller to stabilize the plant. Okay, so that is the solution to the pole placement when we know the transfer function. All right, with that, let's have a break, and then we will find out how we're going to solve the several problem. Let's have a 50 minutes break. All right, welcome back. So let's see where we are now. Remember at the beginning, right, I mentioned the goal is to achieve zero steady-state error, right, to step input. But have we already achieved that? So let's check it out. If we go back to the example 2, and then let's try to find out what is the closed loop transfer function for that example. So here I just write down the final answer. We know that the poles, right, of this closed loop has been placed to the desired ones. Okay, so therefore the whole closed loop is stable. That's not a problem. But let's find out what is the steady state gain or the DC gain. Steady state gain means that, right, if you have a constant step, right, output will be a constant multiply by the input. Given the transfer function, how do we find out the DC gain or the steady state gain? Which value should we evaluate for S? 0, right? S equals 0. That's easy way up. You put S equals 0, you get this one. Hey, you see, that is 2.76. What does that mean? It means if you pump a step 1, and the output will be 2.76. Okay, so therefore, did we achieve steady state 0 to be 0? The difference, right? Clearly, there's a difference. The reference output is 1, and then the actual output is 2.76. There is a gap for us to close. Okay. So therefore, right now, the output of this overall system cannot track the desired step reference input asymptotically, right? So there is something missing still. Okay. So right now we only know how to stabilize, right? Make the whole system to be stable. But at the beginning I mentioned, right, when we try to recall the controller you have learned when you were undergraduate, you know there must be something else inside the controller. We say the servo control, there are 2 parts, right? One is the servo mechanism. The other one is the system stabilization. So we have only solved the second part. We know how to stabilize it, right? And then now we need to find out what is the proper servo mechanism we want to implement to achieve the goal. Okay. For that purpose, let's re-examine this example with a simple example like this. So it's a first order system. Okay. What kind of a controller should we design such that the error signal will go to 0? Of course, you know that there should be an integrator, right? But now let's assume that you don't know that. You already forget that, okay? You don't know that knowledge. We know you don't have that knowledge about to implement those magic integrator. You forget that. So let's start from scratch and find out what is the requirement on this controller to make this error signal go to 0. Okay, so we say, okay, let's just get the transfer function. Okay, let's plug it in. So this is the transfer function of the plant, right? And then this is transfer function of the K, the controller. And then we just reorganize this. This will be the closed loop transfer function, right? This is A times D is S plus 1. N is 1, right? So A times D plus B times N. Right, this is the closed loop transfer function, and then this is the numerator, right? This is the denominator. Okay, we can design A and B. Then we, of course, we are going to design our A and B to make it stable. So this one, this denominator here, all the roots will be to the left half of the plane, right? Negative real parts. Now let's just try to compute what is the error signal, E, right? So we say, okay, we know E is just R, right? The reference signal minus output. So, and we know about what is output. Output is this transfer function, right, times R. So therefore, let's just evaluate this. R minus the transfer function times R, okay? And then we end up this expression, right? Okay, so this will be the error signal. Now remember, right? What is the objective? The objective is we will try to make this error signal go to zero, right? Go to zero when the reference input, right, is a step signal. Remember, the 1/s is the Laplace transform of a step input, right? So let's plug it in. So this is R is 1/s, and this is the term, right, which is 1 minus the transfer function. So this is the final expression of this error signal when the reference input is a step. You just pay attention to this expression. We want to make the signal go to zero, right? Okay, remember, this is the Laplace transform of this error signal, okay? And remember how we're going to find out how going to do the inverse Laplace transform or find out the time domain expression of this Laplace transform. You are going to do the partial fraction, right? Partial fraction, and then so we know, okay, this one, those polynomial we know is stable, right? It contains some stable factors. Those stable factors, of course, the corresponding term, time domain signal will go to zero. But here there is a s in the denominator, right? If s is in the denominator, so which means that in your when you do the partial fraction, there will be alpha over s in the partial fraction, not alpha over x s. This signal will be a constant, right? So you say, hey, how can we make this one, right? How can we make this error signal go to zero if s is in the denominator? If s is in the denominator of the final solution of your error signal, is it possible to make the error signal go to zero? I already tell you it's impossible, right? When you do the partial fraction, this will be the part of your signal. And when you know that one will correspond to a non-zero constant, right? So there is only one possibility to make this E go to zero is you make those S disappear to make it vanish. So how can you make it vanish? Then you look, okay, there is a whole bar in the numerator, A, you can design A, right? So if you put S as a part of A, here are you put A, you design your A in terms of S times A prime, let's say. If you design it that way, this S and S will be cancelled out. Okay. Again, here, of course, some students may object, hey, you know, in some class, you mentioned that you cannot cancel out those unstable factor, right? But here we can because we are talking about a signal, right? For a signal, we can't cancel out those unstable factors. Is that clear? That's the only way that you can make this error signal go to 0. You have to cancel out the unstable factor. Is that clear? If it cannot be cancelled out, that unstable factor will give rise to a signal which will not be 0. Okay, and then you mentioned how about those factors, right? I already mentioned that those factors inside this closed loop polynomial, they're all stable. While when you do the partial fraction, all those factors, will corresponding to a signal which will go to 0. Right? Okay. Now, I think I already mentioned that way. The only way out is put S, right, as a part of your A. But if I include S as a part of A, right, it just means we put an integrator in the controller. You see, this one, S, if I combine 1 over S times K, right, that is the controller. It just says, okay, S will be a part of the polynomial, the denominator polynomial of a controller, right? So now we just look at this problem from a totally different angle. We are not aware that the knowledge you have learned when you were undergraduate, we don't know whether integrator is necessary or not. But from this argument, right, we know we must put S into a part of A to cancel out this S in the reference output such that the error signal can go to 0. Okay, so therefore it means, right, we have to design something into the controller that is the proper servo mechanism we have to implement. Is that clear? Okay, now you can also imagine, right? In this way, we say, what is the error signal when the reference signal is a step? If the reference signal, let's say, just to follow up on this, right? Let's say, if the reference signal is a sinusoid, right? We say, okay, sinusoid, let's say 1 s squared plus 1. I can use the same example to show, okay, which means this one is 1 over s squared plus 1. And we want to make those e equal to 0. We also have to make this one disappear, right? Which means you have to design those s squared plus 1 as a part of your controller. So that is the idea. We have to get rid of those unstable factors in your reference signal to make the error signal go to 0. Okay, so that is the idea we're going to follow for the general solution. Okay, so the servo mechanism determination, we say it is important to find out what are the unstable factors in your reference signal. Okay, we suppose the feedback sets to be stable, right? Let's first, because we know that to get the solution, we want to know what are the unstable factors in the reference signal, and eventually we will try to determine the response to the disturbance, right? We also want to know what is the unstable factor in the disturbance. Okay, we want to cancel out all those unstable factors. And then, in that way, we can achieve the steady state error to be 0. Okay? Therefore, for that purpose, we have to know the Laplace transform of the reference signal and the disturbance. Right? At least may not be exactly right. Exact form is not necessary. We want to know the unstable factors. Okay, let's get the Laplace transform of the reference signal, or Laplace transform of R. Let's use NR over dr. Then we get the disturbance, the Laplace transform of disturbance is NW over dW. Of course, we know in this expression, this denominator of this reference signal or the disturbance, they may have some stable part and also unstable part. If, of course, if the dr or dw is stable, right, the system is very straightforward, right? We know they'll go to 0 anyway, right? It will not affect the output at the steady state. So the only interesting or the difficult part is when we have some unstable factor in the reference input. For example, if your reference input is a step, we know it is unstable. It has a constant 1. Or we know, okay, it probably is a 1. Then we know, of course, it is unstable. There is unstable factor of a squared. Or if it's a sinusoid, we know, okay, there is some unstable factors. So we are only interested in those unstable factors, right? Then, because in the solution, we want to deal with the following isotopic striking problem and also the disturbance rejection problem at the same time. Here, because one student, in the break, one student asked me, okay, you mentioned there are 2 problems. Why is isotopic striking, right? You want to make the output follow the desired one, but when the disturbance is 0, another problem is that, okay, you want to make the output go to 0 when there is a disturbance. They said, okay, are you going to give us the 2 solutions? No. The server console means, okay, the one solution will achieve both objectives. For that purpose, why we need to know the unstable factors of both the reference signal and the disturbance. Okay. Now let's define this common denominator of the unstable modes of the reference signal and the disturbance, and then we use a polynomial Q to denote that. So Q is this common denominator, this common denominator of the unstable factors of the R and W. Okay. And I just show you, right, in order to make the output error go to 0, we need to include those unstable factors, right, inside the controller, right? That will be the key in the design. Why are we going to do that? Because we know that in the final solution, right, of the output or in the final solution of the error signal, we know that the unstable factors, right, will be in the expression, right? And then we have to cancel them out. All right, let's just go through some examples for you to be familiar with how we're going to find out the least common denominator, right? Least common denominator for the unstable factors. Okay, here we say this is the reference signal is a step, right? Here, this is the disturbance. Okay. And what is Q? So what is the least common denominator of the unstable factor? What is Q? If you compare S and S times S plus 1. So if we try to find out the least common denominator, of course, we will compare S and S plus 1. It should be S times S plus 1, right? But because S plus 1 is a stable factor, so we don't care about those stable factor. We know those factor will go to 0 anyway. Okay, so Q actually is only S. Is that clear? Okay, now the second example. So R is 1 over S squared. 1 over S squared means that you try to follow a ramp. Just let's say the time domain expression is T ramp. Then this is the Laplace transform of a ramp is 1 over S squared. So this one is a step. The disturbance is a step 1 over S. What is the least common denominator? What is Q? What is Q? Is Q S or S square? It is S square is least common denominator. Okay, here the another example, right? We have this R will be in this form. You can say that it has a step and also it has a ramp, right? Put them together, right? We only look at the unstable factor is S square. Of course, this one is S. So just similar to this example 2, we know that Q equals is S square. Now, the fourth example, so R is a step 1 over S, but here is a sinusoid, right? The Laplace transform of this sine omega t is in this form. So there is a unstable factor S square plus omega square. Now, what is the least common denominator of the unstable factor in this case? You have to multiply those two, right? Multiply those two S times, because both of them are unstable factor. You multiply them, that will be the least common denominator. Okay. On this one, of course, this one R is just 0. The W is sine omega sinusoid. You get this one. Clearly, this common denominator is just S square plus omega square. Okay. So this one, of course, is that when you want to follow a sinusoid one where the disturbance is 0. Okay, just the same as the example 5, right? The Q equals S square plus omega square. So basically, you try to find out the unstable factor for both. You combine the reference signal and the disturbance. Okay, because now we have to cancel out this Q in the final system. All right. Then, motivated from the special case we just mentioned, right, when we try to follow a step input, if the reference is a step, right, we say Q is S, right? And so if I look at it this way, we know to follow a step, we have to have an integrator, right, in the controller. It means, right, this S, because Q equals S, just say 1 over Q is a part of your controller. If there is a ramp input, actually, we need to have a 1 over S square inside your controller. Also, it just in this form, 1 over Q. If it's a sinusoid, I also just showed you, right, you have to put those sinusoid as a part of your controller. Okay, in overall, so we say when the reference input is a step, right, you have to have an integrator 1 over Q. Therefore, for those one, we can guess the final form, right, or the general form for general input will be like this. We have to include 1 over Q as a part of your controller. In other words, right, in other words, those Q has to be a part of A, the denominator. Okay, that is our guess of the solution. We are going to prove that this will solve the problem. Okay, so that will be the idea. So here, this will be the key to solve the servo problem, right? We want to make the error go to 0. How are we going to cancel out those unstable factors in the reference signal and the disturbance? We say, okay, we have to include those unstable factors inside the controller. Specifically, right, the Q has to be a part of the denominator of your controller. Okay, that will be the solution. Okay, now we want to prove that. Okay, so I'm going to show that. So here in the following, here we try to simplify the mathematical derivation. Okay, so we say, okay, Q has to be a part of the controller, but instead, this one, just to simplify the design or the calculation, we say actually because we already know Q, right? We know the reference signal we want to deal with. We know the disturbance. Okay, of course, you may say, hey, of course, we don't know the disturbance, right? We don't know the exact value of the disturbance, but we know the property of the disturbance, right? If it's a constant, we know S will be in the denominator, right? If it is a RAM, we know S squared will be in the denominator. So that's what you need to know. You don't need to know what are the exact values of those constants or what is the slope of your run. You don't need to know that. Okay. So therefore, from that one, actually we can get Q. We know the this common denominator, right, for those unstable modes, because Q is already given. Therefore, we can put Q. We combine those Q with those system while we have a generalized plant. We put Q as a part of the plant. Then, of course, okay, don't get confused. But we say this is a generalized plant because it is not the plant. The plant is N over D. We put this Q here. It's just for us to derive the solution, right? To simplify the mathematical solution of the servo control problem. Okay. Why we can do that? Because we know N, we know D, right? Of course, because we know the transfer function. And also we know this Q because we know what is the reference input we want the output to follow, right? What type of the disturbance may impact the system. Okay, so Q is given. So that's why we can form this generalized plant. And also we know those generalized plant is strictly proper, right? Because we know the original G is proper, right? And also the Q, as long as the Q is a polynomial of degree 1 or above, this will be strictly proper. Now, what's the second step? The second step is that we have to stabilize this generalized plant. Okay, now you have a new plant, right? With the transfer function be given. And then the proper becomes, how do we place the poles of the generalized plant to some desired position? Okay, now from the solution we gave in part 1, right? What are the conditions such that we have a solution to the pole placement problem? What are the conditions on this N, Q, and D? When can we get a solution such that we can place the poles to anywhere we like? There is a condition, right? What is the condition? There's supposed to be no common factors, okay? So therefore, if N and D, but here we are considering the generalized plant will be D times Q. If N and D times Q have no common factor, then, which means, right, the root of this Q cannot be the same as root of N. They cannot have the same root. I'll give you one example. If you have a system like this, you know that the N has a S, right? But if you try to reject the step type disturbance, right, then the Q will also have a S. Then there is this S and this S, they have a common factor. Those are the unstable factor, right? In this case, it does not satisfy this condition. Okay. then we cannot include our 1/s in the controller. In this case, if we do that, we know the system of the closed loop, right? System will be unstable. Okay, now under this condition, this N and DQS, they have no common factors. We can always find a solution, right? Controller. And this degree of this controller will be N plus Q minus 1, because the degree of this generalized plant is this N, right, plus Q. The order of this controller will be N plus Q minus 1, right? Then we can get a solution. Just follow the solution we gave to you in part 1. You're given a transfer function of the plant. You find out our controller to make the poles of the closed loop to be at some desired positions. Okay, then practically you just specify a desired stable closed polynomial of a degree M plus Q plus L, right? And then try to solve this polynomial equation. You are given DQ, you try to find out A and B, right? And then to satisfy this equation, that is the pole placement we have solved, right? And you know how to do it. So we say that finally, once we found out those Q, right, we'll put it inside the generalized plant, then finally the solution will be converted to how to solve the pole placement problem. If we know how to solve the pole placement problem, then we can solve the servo control problem. Okay. But now, of course, we need to prove that this is the right way to guarantee that the tracking error will go to 0. So now let's prove that. Right? We have the second theorem. So we consider, remember the solution is given, right, for this unit output feedback system. Okay. But of course, if you have if you modify this configuration, right? If you put some other transfer functions here, okay, or you put some transfer functions, right? Here you can see that the disturbance is affecting the output directly, right? So the output is just this signal plus the disturbance, okay? If you have some other things, you can follow the same way to analyze, but the final solution form, probably there may be some difference, right? But as long as you know how to analyze the closed loop and how do we end up with the solution, you can easily do with some other configuration. Here, we just gave the solution in the form of this configuration. This is the unit feedback system. Let's say in your final exam, when say, okay, you design a unit output feedback system, you need to know we are talking about this kind of configuration. Okay. You are given the transfer function and then you are designing the controller. Okay, here there is a condition. We say, of course, the plant itself, right? N and D have no common factor, the coprime. Then we say the Q is the least common denominator of the unstable modes of the set point R and W. We need to determine that. Okay, and if N and D times Q have no common unstable root, then there is a proper compensator K tilde, which can stabilize the generalized plant. If that's the case, then the overall controller, remember, finally, the overall controller will be in this form, will be K tilde right over Q, or K tilde times 1 over Q. That will be the final controller you are going to use. And this controller can achieve isentropic tracking and regulation robustly. Now let's try to approve this conclusion. First of all, the stabilization part, why we have already shown that, right? In part 1, we know there exists a solution to stabilize the whole generalized plant. We just need to show under this scheme, right? The tracking error, the output error will go to 0. So let's try to analyze that. Okay, let YR, right, denote the output excited by R when the disturbance equals 0. Okay, and then we analyze the expression of the error signal. So the error signal will be R, the reference output, input minus the real output, right, which denotes the response J excited by R. We know, okay, this is the transfer function between the R and Y. So we just plug it in. Then this one will be, okay, this R minus this transfer function times R. So we reorganize everything. Okay, we plug in the expression of this G and also the controller. This will be the final expression of this error signal. You look at this one, this part, because the system is stable, right? The system is stable, so therefore, this dq times a plus n times b, this polynomial is stable. All the factors are stable. Now, we have to deal with this factor. This denominator, there are some unstable factors inside this dr, right? We know we want this E error signal go to 0. We have to make those unstable factors disappear in the dr. Now you can see the purpose of this Q. Because all those unstable factors actually will be a part of Q. Is that right? Right? That's how we compute this Q, the least common denominator, right, of the unstable factors of the reference signal and the disturbance. So we can say, yes, we designed the Q just for the purpose to get rid of the final expression of the R, or get rid of those unstable factors. If those unstable factors cannot be get rid of, the error signal cannot go to 0. Okay? So therefore, we'll prove that the error signal will go to 0, right? Of course, you can say, okay, under the condition that the disturbance is 0. Okay, now we prove the second part. The second part is we want to analyze the output of the system when we try to follow the 0 reference output. So R equals 0, but the disturbance, right, is there. The disturbance is not 0. Okay. Now, this is the transfer function. 1/1 plus GK is a transfer function from the disturbance to the output. Okay. And now the reference signal is 0. So 0 minus this one times W. And then once again, we plug in the expression of this D, the expression for this plant and the controller, right? We end up with this expression, and then we plug in the expression of the disturbance. And you will realize, right, again, we want to make this output due to the disturbance go to 0, right? We want to minimize the impact of the disturbance. So I want this one go to 0, and you can say, how do I make it go to 0? This whole system is stable, so all the factors inside this polynomial are stable. We know, of course, the disturbance. There are some unstable factors in the disturbance, but again, those unstable factors will be cancelled out by Q, right? They are included as a part of Q. So they will disappear. The final solution, right, of this E, this error signal will go to 0. Is that clear? But then some students may still ask me, hey, this one, I only show you that, right? If the disturbance is 0 and then there is a input or reference input, we say the error signal will be 0, right? Then the next part, I only show you that when the disturbance is not 0, but the reference input is 0, we show the response will be 0. Now I claim that will be sufficient to prove that when I have both the non-zero reference input and also non-zero disturbance, they will achieve the two objectives at the same time. Why? What is the logic behind my argument? I prove them separately, and then I can claim if I combine those two, I will achieve both goals. What is the principle behind this argument? Exactly a superposition principle. We try to analyze the response of a system, right? If there are two input signals, I can analyze the response of the system of one input and another input. The total response will be the summation of those two if I apply both inputs at the same time. Okay? So therefore, the final solution, right? If I prove them separately, the response of this system for those two separate inputs, now I apply them at the same time, will achieve both objectives. Okay? So the final solution, actually the servo controller will achieve both asymptotic tracking and also disturbance rejection. Now, let's summarize a servo control design procedure. You first, of course, you know the transfer function of the plant. The second, of course, you need to know the type of the disturbance and the reference. Then, because Q is the least common denominator of the unstable factors, right, of this disturbance and the reference. So you have to design Q. Okay. Then you include the Q into the pose of the controller. This is the servo mechanism. So you have to put this Q as a part of the controller, and then the rest because it's just a pole placement problem. You want to make the whole system stable. And with that, you can solve the servo control problem. So this is one way, right? This is the way we derive the solution. So we design the K tutor to stabilize the generalized plant. Okay. And finally, the servo controller will be a combination of this K tutor and 1 over Q together. So that's what I say. The servo control design, there are two parts, right? The servo mechanism and the stabilization. The servo mechanism is, right, to put the unstable factors, Q, right, into the controller. And the stabilization means finally you have to make the overall closed loop stable, right? Because we know if a system is unstable, right, you cannot achieve anything. Now, let's look at example 3. Okay, I have a plant. This is a very simple one. Of course, it's unstable, right? But it's first order system. The reference, we say we want to follow a sinusoid. This time out is no longer a step. This is a reference signal, it's a sinusoid. Then the disturbance, we say the disturbance is of a step type. Look here. So you get the Laplace transform of this sinusoid. Sin t is 1 over s squared plus 1. You get this because with disturbance is a step type, right? It is 1 over s. In this case, let's go through all the steps one by one. What is Q? What is Q? Right, you have to put them together, right? S squared plus 1 times s, because both of them are unstable. Then you form the generalized plant, which means why you put this Q and this G together. Therefore, we multiply them together, we have this. This is the generalized plant. Okay, now we follow what we did for part 1, right? We look at we have to check the order of this plant. What is the order of this plant? 4. So therefore, we know what's supposed to be the order of the controller we should design. If n equals 4, what is the controller? Order of the controller? In part 1, your short-term memory is supposed to be very good. N minus 1, 3. Right? Then we say what the design controller of order 3 can be determined from this equation. Okay, now we say, okay, because this is 4, right? And the controller is 3. Therefore, the desired polynomial should be 7. With order of 7, you need to design 7 poles, right? 7 poles. Okay, in this case, right, we design those poles, right? We say the dominant pole is -1. Those -3 are far away from -1, right? But remember, right, you can design some other numbers. Okay, let's say your questions, if the desired poles are not given, right? Of course, you can choose the simple numbers to compute. If the desired poles are supposed to be designed from some other source, right? You have to follow the design procedure. Here, I just give you, okay, those 7 poles. But remember, right? When I say, you can choose any simple numbers to compute. But if you don't like, the poles of -1, you say I choose s -1. If in your design you choose a pole like this, you will be in big trouble, right? That just means you have no idea what are the poles for the stable system. Whenever, in your exam, if you made those mistakes, right, normally half of the marks will be gone, because that's very bad. That's very bad. Okay. Then you solve this equation. Okay. So you, of course, it involves many equations. You say there are 8 equations. There are 8 design parameters. You can solve them. You get A and B. Okay, the K tilde will be a third order system, right? And then the complete servo controller, actually you have to add the Q. So finally, what is the order of the overall controller? This is 3. There's another 3, right? Order will be 6. 3 plus 3. Now, but we want to know, is it possible to reduce the order of the controller? We want to simplify that. Okay, actually, there will be another simplified design procedure for the servo control. Okay, The first step is the same. Of course, you need to know the transfer function of the plant. The second step is also the same. You have to know the Q, right? Now, the third step is different. You see, in the first design, we form a generalized plant. Then we try to stabilize the generalized plant. Okay, now, actually, we don't need to do that. We can just directly include Q as a part of A. So in other words, you design the A in this form. So you say, okay, the A has to be a Q times A prime. And then you solve the power placement problem by directly plugging the expression for A prime and B, right, inside this equation, and then you try to match the coefficients. Now, let's use this procedure to solve the example again. We know, okay, this one, and then we know, okay, what is Q? It's the same Q. We want to follow a sinusoid, right? And then when there is a disturbance. Now here, I directly say, okay, my A, the denominator of my transfer function has to include Q, right? And also, we know, okay, we want to have more design parameters. I also want to design a one polynomial. So I make this whole controller with an order of 4, right? This is 3, Q is a degree of 3, another one first degree polynomial. Okay, since this one is 4, okay, now we know that, of course, the degree of B cannot be bigger than 4, right? So to make it simple, okay, we just choose the degree of B to be 3, make it strictly proper. It is not necessary to be strictly proper, or you can make it proper, but in that case, you have more design parameters. Okay, here, I just make it 3, and then I plug into the equation. So A times D plus B times N, because we know this is the form of this A, we already included Q, right? We have this S plus A naught, then we have this S minus 1. This is the D, this is B, this is the N. All right, normally, when you notice there is some stable factors in your transfer function, right, you cancel out the stable factor. Normally will simplify the design. So, okay, so this is one trick. You always want to cancel out the stable factor to simplify the calculation. So S plus 3 is a stable factor. Here, we want to cancel them out, which means you put the stable factor inside your closed loop polynomial. So S plus 3 will be a part of your closed loop polynomial. Then the other poles, right, we put them as -1, right? You plug them together. Then, because the total order is 5, right, you need to design 5 poles. One is already -3, the other are -1, right? And then, of course, to cancel out those S plus 3, this polynomial has to have S plus 3. That will comes from this S plus A naught. So put the S plus A naught as S plus 3. Therefore, essentially, we already fixed the design of A. Then we plug it in. Okay, so we plug it in, and then both of them have this common factor. We take it out, right? And then this polynomial is up with a degree of 4, right? And then there are 4 coefficients. But here, the desired polynomial, you look at this one, has a common factor S plus 3. But if you look at this polynomial, there are 4 coefficients to match, because the leading coefficient is automatically matched, right? 1 and 1. Therefore, you have 4 equations. B naught will match 1, right? B1 minus 1 will match 4. B2 plus 1 match 6, B3 minus 1 match 4. Easily you can get the design parameters. Get those B. That will be the solution for this design. Then you can you look at the solution of this controller, right? Easily you can get the order of this controller. So what is the order of this controller? 4. This controller is much simpler than this one. This controller is 6. Now the current solution, right, will reduce the order. We have a simple solution. Okay. Okay. When you try to solve the problem, right, it doesn't matter. Okay, let's say you want to get the solution. You can either, I give you 2 ways, right? The second way normally, right, the calculation will be simpler. But it involves some tricks, right? You want to cancel out those stable factors, right? I mean, and you follow that, it's kind of a shortcut. You get the solution. But I know, some students don't like those shortcuts. They want to follow some very systematic way, right? You can follow the first one, right? You can also get the solution. Okay. Now we can go back to the antenna, right? The satellite antenna control problem. Now we can give the solution to that. We know this is the transfer function. This parameter A equals 0.1. So, and then this would be this transfer function. Okay, here, remember, right? This disturbance, right, is in this form, is this transfer function times D. But we know in this configuration, the disturbance is just directly added to the output. So therefore, this supposed to be the disturbance we should use. We don't use this little d, we should use this W. It's the combined one. Okay. All right, so what is Q? Remember, because the reference is 1 over S, the disturbance, right, has a S squared in the denominator. So therefore Q is S squared. And then I'm going to show you the 2 ways. One is the generalized plant. Okay, you follow the first way will be of order 4. Then you design controller with order of 3. Okay, and then you say, okay, I'm going to choose the poles, right? With the 7 poles, you design that. You match the coefficient to get the solution of A and B. Will be a 3rd order, right? Polynomial. That will be the controller to stabilize the generalized plant, but the final controller will be combine this K tilde and this Q, right? This one with the order of 5. Okay, now, and then when we do the simulation, this will be the closed loop response. And yes, if I look at the steady state error, right, it can track the response. Also, there may be some disturbance affecting the system at this point. But finally, the output will go to 1. So the accuracy is okay. It's just that this one, there is a huge overshoot, right? 100% overshoot. Now, let's try the second design, simplified design. So we don't form a generalized plant. We just say, okay, since, okay, this Q is S squared, but the open loop system already have a 1 over S, right? The plant has a 1 over S. So thus, the controller actually only needs 1 integrator. So therefore, with that information, we say, I'm going to design my controller in this way. There is a 1 integrator in the controller. Now, then we try to stabilize the whole plant. Once again, right, whenever you have a stable factor in your plant, you try to use some cancellation to simplify the design. So we say, because 10s plus 1, right, is a stable factor in the transfer function of the plant, right, we put it inside this k tilde to cancel out. And then we also design another polynomial. We want to design this k1s plus k2. Then we put it in. So this is the open loop transfer function g times k. Okay, and we know that the common factor already cancelled out, right? That stable factor 10s plus 1 already cancelled out. So eventually, this will be the form. Now we have s squared because remember, right? This g. Just recall this is the g 1 over s times 10s plus 1, right? 10s plus 1 is already cancelled out. We have 1s over there, but there is another s, right? Contributed by the k. So this will be the open loop. And then the closed loop transfer function, of course, is just gk over 1 plus gk. From that one, we can get this will be the quadratic polynomial of the closed loop. It's just a quadratic one, second order system. Then easily, let's say, I just pick k1, k2 equals 4. Then I can place the two poles at -2. You can say the design is much simpler than the previous one, right? Okay, let's say, of course, if the controller is in this type, right? You see, this one actually is a PID type. And then you do the simulation, you can notice there is a significant improvement in terms of the overshoot. Okay, and of course, the steady state error will go to 0, right? The two response are the same for the steady state. The difference lies in the overshoot. So the second design is simpler and also is better. But now, of course, there may be a question, right? The PID in its ideal form, you look at this PID, is it proper? This is proper, this is proper. How about this derivative term? Is this a proper transfer function? So you can say actually, although PID has been, you have learned this PID a long time ago, but now you may realize that this one actually, the theoretical PID, there is a problem. Because that's why in the industry PID, you don't use KD, you replace those KD by a proper transfer function like this. Okay, to make it proper. This is what we call industrial D control. Okay, but let's say you want to use a PID, this is acceptable. So although I mentioned that your controller should be proper, okay, but there is one exception, okay. If you end up with a PID controller, although it is not proper, but is acceptable answer. Okay. Now, finally, let's just talk about how we're going to deal with the multivariable integral control, right? We just finished the case where there is only single input, single output. Now, how about multiple input and multiple output? Can we apply the same design directly to MIMO system? Well, because the output will be affected by all the inputs, not just one input, but you have a multiple input, and also there are multiple output. So we need to use the state space approach to deal with the multiple input, multiple output system. Unless the system can be decoupled. So we are going to investigate when we can decouple the system such that the multiple input, multiple output system can be simplified to single input, single output. But I will leave it to next week. So today, we're going to directly deal with the MIMO system. Okay. Here, specifically, we're only interested in the case where the number of the inputs is equal to the number of outputs. Therefore, we have a system, right? Given now we are looking at the standard state space equation. So you have this ABC, but in addition to ABC, we also include the influence of the disturbance, BW here. Okay, we define our arrow vector. That is the difference between the reference input and the output. Now this E is no longer a scalar, right? It is a vector. What is the objective? We want to make this arrow, like all the tracking arrow, go to 0, not just 1. Okay. First of all, let's say what would happen if we just use a simple state feedback controller, right? This is what we have learned in the past, right? The state feedback controller, in general, it will be in this form. Let's plug it in. Plug in this controller into the system. We have this closed loop. Okay. And let's say if there is no disturbance, right? And then actually it is possible to design the K and F properly such that the output may follow the reference signal R. That one it is possible. However, because of the disturbance, if we just do it like this, if we imagine, right, we want to make those X go to 0, right? We want to make those X go to 0, which means that your reference is 0, right? This is 0. And then we design the controller in this way, right? What we can achieve is that the system is stable, right? The closed loop is stable, but will be affected by our disturbance. You can imagine that this disturbance, let's say, is a constant disturbance. What will be the output? The normally that the output will be a constant, right? You have a stable system, you have a constant input, the output will be a constant. So therefore, you cannot achieve the goal. We cannot simply use this design. Is that clear? Because we have to include the influence of the disturbance, right? We have to deal with reject the impact of the disturbance. Or in other words, actually, we need to have the proper servo mechanism. Okay. Now, we know that for the single input, single output case, the servo mechanism is to include an integrator, right? But here, of course, due to time limitation, we can only discuss the case where the reference input is a step type or a constant. We try to follow a constant. Of course, for the different outputs, they may follow different constants. Okay, the reference, just say the reference is a constant vector. The disturbance will also, there's some constant disturbance. The values may be unknown, but it's a constant. We only discuss this type, and then we try to achieve under this condition, right? How can we make the output follow the constant desired output asymptotically? Okay. And we know that for the single input case where we need to use an integrator. Here, we also need to use integrator, but we know, okay, there are multiple output, so therefore we just define a multiple integrators. Here, remember the arrow signal is a vector, right? So therefore, the integration of all the vectors, of course, it is also a vector. V is a vector. Okay, and now if we use the expression of the output, we can get because of this V is the integration of the arrow signal, so V dot equals E, right? But E is just the reference minus the output, right? This one is a vector, let's say, but Y is an output, so it's C times X. So we have a equation for the signal V. Now let's examine the equation of the dynamic system. We know X, right? X dot equals AX plus BU. If the controller, right, will contain this signal V, then the dynamics of the state vector will also depend upon this V, right? Because the input contains this one. Because we know we have to put the integral signal as a part of the control. Okay, therefore, if I put the original equation, this X dot equals AX plus BU plus BWW, right? Together with the equation of this V, we have a augmented system. Okay, well, X dot equals AX plus BU plus BW times W, and we also have the equation V dot, right? We put them together, V dot equals, because we have minus CX, so here we have minus C times X. All those are zero, those all are all zero matrix. So, and then, but because V dot, what, is related to R. So that's why eventually here we'll have to put this R as a part of the equation. Okay, then we have a new dynamic system, and the state of this dynamic system include not only X, but also V. We define this XV, a new vector, as X bar. Okay, so this one is X bar, so we have X bar dot, right? The change rate of this X bar dot, this whole matrix. We have a new matrix that corresponding to A bar. This one is X bar. But here, of course, we have a control vector is B at 0, that corresponding to B bar. And then there are some other input, right? So here is the disturbance. That is the reference input. Okay, but we know those W and R, they are constant type. How about Y? So Y we can also write in terms of C bar times X bar. Okay. Then this time, because we're looking at an augmented system, first we want to know whether the system is controllable or not. If it is controllable, then we can move on to stabilize it. Okay. So here you can check the controllability matrix. Right, controllability matrix will be this, you know, B bar, right, and then there's A bar times B bar, right, and then there's A bar squared times B bar, right. That's you use the same definition as the controllability matrix we have learned before, but here you have to use the new matrix. Instead of ABC, you are going to use A bar, B bar to check the controllability matrix. Here QC, but this one can be written in this form. Then you check, okay, this is controllable, that this actually, as long as the rank of this one is 4 rank. And also this one, because this one is controllable, this matrix is 4 rank. It can be proven that both matrices are 4 rank, and then this whole system will be controllable. Then because the whole system is controllable, right, augmented system is controllable, then we know either from the chapter 7, right, or chapter 8, you can stabilize it. But here, when you design the state feedback, you know that this state vector is the augmented state. X bar include both X and V. So here actually you can analyze the expression of this controller. The controller include 2 parts, right? One is minus K1, this is a matrix times X. Another one is minus K2, also is a matrix times the integral, but integral is a vector. So in other words, this is like a PI controller, okay? But you can interpret it in this way. But remember, right, it's not a typical PID controller you have learned in the past, because we are talking about, right, there are multiple variables here. But remember, we can always design this K to stabilize the whole system, right? So how we going to compute this K? You can either use the power placement, or you can use the LQR. Okay. Now, let's analyze the closed loop system. So let's plug in the feedback controller, right? So in this closed loop, there is no more U, because U equals minus K times X bar. We have this one, but we know I choose my K1, K2 such that this matrix is stable. A bar C will be stable. I don't care whether those are the factors were related to the disturbance and the reference, but we know they are of step type. It's like you say there are some constant inputs affecting the stable system, because this one A bar C is a stable matrix by designing a K1 and K2. So the whole system is stable, right? The whole system is stable. Of course, it does not mean that the X will go to 0, right? X bar will not go to 0 because it has some impact from the disturbance and the reference. But we know the whole system is stable. That is the key part. As long as we have a system is stable, right? And then we say, hey, there's some input signals, right? Either is a disturbance, W, or some R is also some constant. There are a constant inputs affecting the system, but the whole system is stable. So therefore, at the steady state, eventually when everything settles down, all the signals will go to some constant, right? For a stable system, you have some constant inputs. Finally, all the signals will settle down to some constants. It will not blow up. Also, it will not, change to some sinusoid or some other things, because the inputs are constants. Is that clear? So that is the key part to understand the final answer. The whole system is stable. All the signals will go to constant. Okay? Well, because V is a part of the state, right? It will go to constant. What does that imply? If V is a constant, the V dot will be 0. But what is V dot? V dot is the error signal. You can see the error signal will go to 0. Okay? Any questions? So that is the way we can track a constant step. Okay, you can see that the servo mechanism relies on the magic power of integrator again, right? The input to the integrator must be 0 when everything settles down to a constant. Well, you may wonder. Now I only talk about the case when we try to follow some constant reference signal, right? How about other? What happens if the reference input is a sinusoid? Can we use the same way to deal with sinusoid? If the reference signal is a sinusoid, can we just use this one to make the output follow the desired output? Or can we make those error signal go to 0? You cannot follow that, right? Because, right, for a stable system, if our input signal is a sinusoid, eventually all the signals will be sinusoid, right? Which means, right, all the signals will be sinusoid. The output of this integrator will be sinusoid, will not be constant. If the output of integrator is not constant, there is no guarantee that the input signal to this integrator will be 0. So therefore, we cannot use this simple way to solve the tracking problem when the reference is a sinusoid. This is also true when we try to deal with the single input, single output system, right? We have to put some other factors. Okay. Of course, this problem has already been solved in the textbook, so we don't have time to discuss that. It's more advanced. It can be solved for other type of reference input. Okay, so finally, let's just quickly go through a final design example where we have an integral controller. We want to design an integral controller to track, right? The output, actually the output are the 2 state variables. So we want to track, we want to follow 2 desired outputs, right? 2 state variables. Of course, you can check this original system is controllable. And then we check, we can get the augmented system. Now the augmented system is a 4th order, right? It's a 4x4 matrix. This is A bar. Then this will be the C bar. Okay, you should also check whether the augmented system is controllable or not. Of course, it is controllable. Well, and then you design the cost function. Remember, this cost function, in that form, you have to put the augmented state as a part of your cost function. So therefore, the dimension of the Q, right, will be a 4x4 matrix. The R, of course, is 2x2. Okay, and then you know those Q and R, and then you know those A bar. Remember, you can see in this Ricard equation, you should use A bar and B bar. So everything now you have to use the numbers from the augmented state, because you want to stabilize the augmented state, not just stabilize the original system. If you do it in this way, you follow that. Okay. For the simple way, when this Q and R are identity matrix, you will get a solution K. Of course, if you use MATLAB, right, there is a command in MATLAB to do that, solve the Ricard equation. It's called I-care. And also here, I gave you a Simulink model. Right? I would suggest you build your own Simulink model, probably follow this way, probably follow other way to reproduce the result here, show you this example. Try to do that because in your mini project, right, you have a more complicated system to deal with. is 6. The order of the system is 6, right? But anyway, for this one, you do it, then you can say this is the result. That let's say if I want to follow, there are 2 outputs, right? I want both of them to follow a constant step. You can say eventually those 2 outputs will converge to the constant step following the integral control. All right. So let's summarize, right? What's the object of servo control? We want to track a time varying desired output and also want to deal with the disturbance. How many ways you have learned? 2 ways, right? You can either use the transfer function if there is only 1 input and 1 output. If there are multiple inputs and multiple outputs, right, you have to use the state feedback. But remember, doesn't matter which way you use, there are always 2 parts in the solution. You need to know how to stabilize the whole system. You need to put some servo mechanism as a part of your solution. For servo control, finally, does the state feedback controller take the same form as in this one? Right, not exactly. There is a change in the state. The state is no longer just x. The state includes both x and the integral. Okay. All right. So it's our long lecture. So that's the end of today's lecture. I will see you next week.但是这2种方法是可以说这个方法同样的，这个方式这个方法我故意要讲不同的方法，看过2种方法，2种方法，不一样的，不一样的。我也没有时间用了，我没时间用。如果弄里面的还有啥？但是重要的是他们之间的，重要的话是他前面形式，他几个都是引猫追鱼，那个是一样的，他那个这个东西不一样。不是你自己选的，每个人不一样啊。每个人这不说了吗？你每个人用自己的，当时就不一样嘛。对呀，你不是你自己选，你的麦克只能用你自己的麦克去上面。明白了吗？我这么做就是每个人做的答案肯定是不一样的，对不对？你如果跟你比如说你有个 group， 对不对？你们最后做的还是自己做自己的，对不对？你们可以讨论，对不对？但是2个人solution一样，我们一眼都看得出来，因为你们学校不一样，肯定是应该不一样的。我就是觉得这个东西是一个答案是你自己的。那除了前面这个 model 可以啊，可以啊，就是可以，那没问题。老师前面2节课讲的是规分跟
个 transient response performance，那这节课讲的是
最后的 output 要达到
要跟随那个 reference，
对，
而且不能受那个 disturbance。
对，是。
但前2节课方法跟这个没关系。
怎么会没关系啊？因为你一定要做 stabilization 的，对不对？就前面2节的方法就是要用你做 stabilization 的。
对。
那今天我讲了另外一种 stabilization， 对不对？就是你如果是用那个传递函数的话，
就跟
transfer function 做 stabilization，
就跟那个 state 那个啥就。
对 transfer function 就是那个你不需要用 state space model。
好。
Which one? This one is 0, right? 0. No. I mean, it has to be 0 because you look at the retardation. Right? Everything should be 0.
I'm not sure you say follow the lecture note, but the lecture note is this issue.
Right. Probably in the typo.